All right. Hi, everyone. Thanks a lot for attending, first of all, and thanks for being here. So, I'm Rashanjyot. I work as an Android engineer at OK Credit. And today we'll be talking about performance improvisations using SQLite. And we'll also touch base on most commonly used libraries and frameworks and the most popular library choices that we have in hand. So, let's get started. All right. So before getting started, I would like to mention this as a prerequisite. This talk requires, or at least requires, a sense of familiarity with databases before, and preferably SQL databases. There might be certain terms that some of the people who are not aware with databases might be readily uh, aware of. We can take that up in the questions later on if there's anything that we miss out on. Anyway, I'll try to get started right from the basics and cover up as much as possible. All right. So first of all, second, right. So while we talk about databases, right, before moving on any further, we need to understand why do we need performance optimizations. So optimization is generally a battle where there's always something that could be done in in a better way, that could have been done or that could be done. So depending upon use case to use case, there might you might need to ooze out last inch of performance, right? And there are two primarily reasons, especially in the Android ecosystem, that this is needed. Apps are increasingly storing more and more data, and they are becoming offline first. Secondly, screen refresh rates are continually speeding up. So the faster we can get the data up to the render, to the UI, that's even better for the user as a user experience, right? So we'll start off with indexes, because probably the first thing that comes to anybody's mind when getting the results faster from the database is indexes. I'll just give a formal introduction to what indexes are. And an index is nothing but a data structure that speeds up the data retrieval operations on a database. But there is an additional cost of writing and storage space needed to maintain them. So in this talk, primarily we are going to cover how are indexes created, why do we use them, what are the pros and the cons, and what sort of indexes can we utilize, particularly in terms of SQLite. Okay, so I didn't want to keep this talk much technical or more in terms of the code. I wanted to address this in a real world scenario. So just think of database tables as pieces of paper where you would write down some information. And now let's talk real world, and let's assume this real scenario. Let's say you're leaving the town and you wish to note down the phone numbers of all your friends, and apparently you live in an age where you need to write it down on a pen and paper, and you don't have a phone, right? So pretty easy, straightforward. Apparently you have three friends, you write them down, pretty easy, right? Now let's assume a scenario where Jake, one of your friends, has a second phone number too. Now if this would have been written on a piece of paper with a pen, the end result would have looked like this. You would have entered Jake's second number at the end, right? So far so good. But what happens when this list grows huge, and over time some of these numbers change, some people get new numbers, some people discard their old numbers? What happens then? In that case, your list would soon look like this, and that's going to be pretty cluttered pretty quickly, right? uh, and what would essentially happen is, when you start searching for Jake's number, probably a few months down the line, you are probably going to have a difficult time doing that, or you're potentially going to spend a lot of time. So it would have been really great if we could arrange the data in a particular fashion, maybe let's say alphabetical order, or we could add rows in between, or update numbers in a particular row, just as we do it on a computer, right? So this is where indexes come into action. So think of it like, since database tables are like physical pieces of paper, and they have and the data stored continually in the order of physical memory. Indexes help you to store data and information in continual order of logical correlation. And logical correlation, simply put, is basically just a sorting logic. For instance, here we want the names to be stored in an alphabetical order. This particular logic is something that you can change based upon what your use case is, right? So the pros and the cons. pretty simple, just as we considered about the within the example right here. If you wanted to, if you look at the GIF right here, right? So if you have to arrange them alphabetically, add in new rows, update existing rows, it's probably going to take some effort from your end, right? So indexes, while they speed up the data retrieval time when you want to fetch the data, they also consume some space, and they also slow down your insertions, updations, and deletions, because they have to be maintained by the database and that sort. So do your own due diligence, and depending on a use case, figure out what's best for you. But if you can but a good rule of thumb is that if you can figure out a logical correlation between the data, and you would generally want to refer to it, uh, given certain set of conditions, you'd probably be better off creating certain indexes. But again, there's no silver bullet. Now, regarding the scope here, we'll only stick to SQLite in particular, because different database systems, especially the modern database systems, have different sorts of indexes. But currently, we're sticking down to the scope of SQLite and Android, right? So SQLite supports and stores indexes as B trees, balanced trees, which is the data structure behind it. While we'll not go into the implementation detail here, because certain different databases systems have different ways to implement them. But here's a very great link that I would certainly recommend you to have a look at later after the talk, which explains how B trees actually work under the hood. Now, before moving on, and while we talk about different indexes, let's consider a sample problem. Again, we want to keep it very much real world, very much correlated to the real world. So let's say there's a use case where you have a transaction, and this table has a few columns: an ID, which is a unique identifier, a sender, which is the name of the person sending the money, a receiver who's accepting, the name of the person who's receiving the money, payment mode, whether it was made from a credit card, debit card, internet banking, or cash. Amount is nothing but the total amount of the money transferred. So we have this table named as transaction, and we'll be using this all throughout to uh, figure out which index to use and when to use, given we have certain set of use cases. Right. So first off, we'll start off with the most basic one, which is the single column index. And as the name fairly suggests, this index works on a single column and stores values sorted on that particular column's value. Right. So let's take the simple example. If you want to find all the money transfer initiated by a particular person, let's say you want to know that your what all transactions have has your friend Jake made, right? So you can create an index. The syntax is there on the screen. I'll not focus much on that. But what we'll focus on here is, of course, another disclaimer here before moving on is that I have used a sample set data under certain different control environments and conditions. So exact values with the data sets, even if used across systems and environments, would change. So everything about the performance here, for example, this shows 53 milliseconds without index, and with the index it shows 1 millisecond, is only indicative of what of the direction this will help you with, and is not concretely objectively written. Right. So back onto single column index. So let's say you create an index on the sender column. So if you run this query without the index, and I can give you a brief idea about the dataset use. It had roughly 10 lakh 10 lakh rows. This was done on M1. This was performed on an Intel i7 MacBook Pro, and essentially. Uh, yes, there was an even share of transactions for all senders and receivers as well. So without index, this query took 53 milliseconds, and with index, it took near about 1 millisecond. And in fact, on recurring calls, it even took even lesser. Right. So this is what single column indexes are about. Uh, and now one more thing to consider here is, while we can see from the time that the time has certainly improved, how can we certainly know for sure whether the index was used or not, or was there some other reason? So while this does not just apply for single column, this is just to understand how a database system actually executes query. There is something known as a query planner, And here and in the following examples as well, we are going to use something, a prefix. You can add this as a prefix to any query, which is explain query plan, and it'll share the details as to which index is it going to use, or even if it is not going to use any index at all. So when we run this query with this prefix, right, and we don't have any index, so the detail you can check, you can figure out in the details that it just simply does a sequential scan on the transaction table, and that's why it took 53 milliseconds. However, with the index, it mentions that it'll search the table using that index that we had created before, which we had mentioned here. So this is how this becomes much more performant. Now let's move on to right. Another thing, if you want to know more about query planning, check out this great link. This is another great link. Uh, right. So now I'm talking about multi-column indexes. These are also known as composite indexes. And as the name suggests, instead of one single column, now these work on multiple columns. Now, one thing to especially note here is that the order of columns is absolutely crucial, and we'll soon see why. So similarly, just as we created an index before, we ran this query for a particular sender and a receiver, where the use case was to find all of the transactions where sender was Jake and and the receiver was Ajay. So for this, without index, the query ran again in 55 milliseconds, and with index, it was fairly too slow. With index, it was fairly too quick that the value came much under 1 millisecond, and hence it shows 0 milliseconds right here. Now, why is the order important? Let's consider this case. Uh, if the columns in the index would have been in the order sender and then the receiver, the data would have looked like this, where sender is first sorted alphabetically in the ascending order. Let's say it was stored in, let's say the index is storing the data in an ascending order. The sender would be sorted first, and then and for a particular sender, all of those receivers would be sorted then. However, if we reverse the order of this, in this case, receiver would be sorted first, and you can see here, instead of uh, sender being sorted first, Jake comes before Ajay, which is alphabetically in the descending order. So here receiver is sorted first, and then all of the values for the sender column for a given receiver are then sorted. Hence, this is transitive in nature. So make sure that you check whether the order of columns that you have defined is as per your requirement. Right. Now, let's talk about partial index. Partial index is an index, formally put this, partial index is an index over a subset of rows of the table. Essentially, if I have to say, it's similar to what indexes we have talked before. These could be multi-column, these could be single column, but they essentially have a where clause in their definition. What this means is, we'll again consider the real use case here. So let's say we want to know beforehand. Let's say you already have a use case where you want to beforehand know whether we would, whether we would want to fetch senders senders of certain transactions where the payment mode was cash, and we don't want to fetch transactions where the mode was credit card or debit card or internet banking, right? So if you already know this, so you can create an index with a clause, and for any row of the table which qualifies this condition will be indexed. Now, let's take an example as to when querying for non-cash payments and cash payments would become different, and what will be the end result. So while querying for non-cash payments, we can see from the query plan that the database query planner would execute a sequential scan instead of using the index, and hence the query would be much slower. However, for cash payments, since we have already set up the index, it will use this index. Now, the question arises, why don't we just index the whole table? Just if you remember the cons that we discussed earlier, right? We indexes negatively impact the performance of writes, updates, and deletes, and also they consume more space. So if you're already sure that you would only need to index only certain parts of rows given they fulfill certain conditions, uh, then you should go for a partial index. So they help you save some space and improve performance during insertions, updations, and deletions. Uh, an important thing to note here is that this value is not going to be absolute. the impact delta is going to be in terms of the performance. In terms of performance, would depend upon um, the ratio of rows that are to be indexed versus the number of rows that are not to be indexed. A quick fair case that I can recall from a real world is, in case you have a lot of null values and you only want to index non-null values and null values are not relevant to you, you can probably index only the non you can create a partial index that indexes only the rows that contain non-null values. All right. So now we'll talk about expression-based indexes. So uh, index, let's consider this case. Let's first of all add another column to our existing table, which is tax, right? And now, let's assume that anytime a receiver is sending money to a sender, I'm sorry, whenever a sender is sending money to the receiver, uh, for any given amount, a certain percentage of tax has to be paid by the sender. So now let's say we have a case where we want to find out the top n number of transactions in terms of the total amount, where the total amount is defined as the value for the column amount plus tax. So expression based indexes are ways to index certain expressions on one or more table columns. You can perform operations such as absolute, floor, uh, length of strings. So you can perform certain operations on the existing column values on one or more of the column values. So here in this case, we would create an index, and we would create this index in a manner such that uh, whenever we want to query for net total amount, and uh, we would run this query select total amount from transaction, where the total amount is equal to amount plus tax. It will utilize this index and it will be a lot more quicker. Right. Now, the last sort of index that we want to talk about today is covering index. Uh, just as other indexes had to be defined, covering index is not essentially something that you need to define. Covering index is more of a mechanism that runs under the hood. Now, to understand this, let's take an example. Let's say we had set up a single column index on the amount column because we had a requirement that we want to fetch uh, the largest or the lowest amounts uh, in all of the transactions. So this index will store the values of the amount column, right? And essentially what happens under the hood whenever you write a query to a table, first of all, if it can utilize an index, it'll go to the index data structure. It will perform a binary search, and it will figure out the position of the index. And then using the row ID values for the actual table, it'll make another query which will run another binary search on the actual table. So under the hood, there are two queries running. So covering index is the case when all of your data that's needed by your query is returned and contained within the index itself. So let's say you just want to query, if let's say we have this case where you want to know what is the highest amount that has been transferred amongst all of the transaction data that we have. And since you have a single column index on the amount, uh, there is no need to query the actual table, and on this data would be directly returned from one single query from the index data structure itself. So covering indexes could be great, and you don't need to explicitly define covering indexes. But if you're consciously aware and if you can set up indexes in a manner that all of your data can be provided via indexes, you'll save a lot of you'll improvise a lot in terms of performance, since a query to the actual table will never be made. Right. Now, up till here, what we talked about uh, was fairly common across most SQL databases in terms of the information. Uh, now let's talk about the Android ecosystem in particular. Uh, something to so something to just a second. All right. Right. So regarding the Android ecosystem, one popular library that we use as an ORM over SQLite is Room. And for this talk, we are going to scope it down to Room and not going to talk about other third party or any other common libraries or ORMs used. So at the time of writing this, Room does not support all of these indexes out of the box. So currently Room has support for single and multi-column indexes via field level and entity level annotations. When I say field level, it's essentially let's say within the transaction table we had defined multiple columns, right? So every field is one column, and you can define indexes on the field level via annotations that that Room currently provides. Or you can also add entity level annotations where you will be able to add multi-column indexes as well. However, as of now, Room does not provide support for partial and expression based indexes, and you will have to resort back to SQLite queries and handle them manually in terms of initializations and migrations, just as we used to do it way before, probably using SQLite open helpers or any alternate libraries that we used earlier in the past. So, this is still going to be a hiccup in that sense. Also, one more thing to take care of is that every Android API level supports a different version of Android SQLite. So make sure, and this is not about just indexes, but anytime that you're adding anything to your code base, please make sure that you're aware as to whatever you're adding is supported by the API target levels for Android that your app essentially targets. All right. Now let's talk about a potential issue in the reactive world. Uh, I've so Now with Room and other libraries supporting reactive queries and reactive programming becoming quite popular, and and developers using reactive streams from such as RxJava, Flow, LiveData, etc. Writing database queries pretty much the norm. Now there is a very big there's a very big potential issue that could pop up and could easily be overlooked if if not taken care well of. So let's talk about and to begin with, this issue might happen under certain circumstances only, and to understand those we'll have to have a deeper look as to how reactive queries work internally. We'll stick to Room as the scope for this to understand what happens under the hood, and then we'll get to the root of the problem and see how to fix this and when can this happen. uh, all right. So before moving on, we need to understand what database triggers are, because under the hood, Room generates code to utilize database triggers to run reactive queries. So triggers are nothing but database operations that are automatically performed when a database event occurs. So simply said, whenever an insertion, updation, or deletion happens, and then there are different set of cases. For example, before insertion, after insertion. So any time any such event occurs, uh, triggers can be executed as pieces of code which you would want which you would want to essentially execute given certain of these events occur. Now, I guess Room DAOs are pretty popular, so I'll just talk about those. So DAO, whenever you define a DAO, it essentially whenever you annotate a DAO in your code, it generates code for a reactive query in a manner that it internally observes any changes made to the table. And one thing to note here is that database triggers work on table level and not row levels, and that is why anytime Room gets an update, or anytime Room gets an update about data being changed, it just knows that something in the table has changed but does not know which row has changed. So it just know the maximum granularity that we have here is on the table level and not on the row level, and this is what causes this issue. And we'll see how. So we you can also have a look at what sort of code does RoomDAO actually generate. You can see in the bold that there's an invalidation tracker, and this tracker and essentially the code that is generated subscribes to this invalidation tracker, and whenever this table gets invalidated, and this invalidation essentially means any update, any insertion, or any deletion has happened to that table, uh, Room will fetch fresh results from the database and send them back to the subscriber. Uh, And also here's a great link of a blog post that describes how SQLite triggers work and how room internally gets affected by these. If you want to have a look at a much deeper level, you can refer to that. Now, so far so good. When does the problem arise? That is something that we have to take care of and understand. So let's consider this use case. Let's assume we want to implement a query, a reactive query that returns a list of transactions for whom the payment mode was cash and not credit card or debit card or internet banking. So this is how we define a DAO and write a reactive query. In this example, we are using Kotlin Flow. Now, given this query is subscribed and a new transaction is added to the table with the payment mode as credit card and not cash. In this case, the result of this query would not essentially change, because if there were 10 transactions of type cash, after an addition of a transaction with payment mode as a credit card, the number of queries and the data of all of those queries with the payment mode as cash would still remain the same. However, since database triggers work on a table level, what would essentially happen is this would re-emit the same data, but as a fresh new emission, and all of your code will essentially get activated again and start processing if this case is not dealt with. Now, how do we deal with this? If you and let's take a real use case for this. Let's say you have a list where you're showing, you have a list on the UI where you're showing these cash transactions together. Now, whenever this insertion of credit card transaction happens, essentially you should not re-render that list of cash transactions, or your processing all throughout your code should not happen again, because essentially the set of the list of cash transactions hasn't even changed. So to avoid this, most of the popular reactive streams implementation do provide an equivalent implementation of some of sort of a caching mechanism, where it checks whether the last emitted data was same as the current data or not. So for RxJava and both Kotlin Flow, the name of those is similar. RxJava has this operator distinct until changed, and Kotlin Flow has an extension function with the same name. And what it does is it stores within itself the last emitted value, and then whenever there's a new emission, it checks if new emission has arrived. This is something that we can figure out from this marble diagram as well. For example, for the first time one was emitted, one gets emitted. For second time, value changes to 2, and second and 2 gets emitted. But if the value doesn't change and something else changed in the database, this time it won't get emitted. So this is something to be taken care of, because this could potentially consume a lot of processing power. And since queries are reactive, this could have a multi-fold performance degradation in your app. Right. Now, the last thing that we want to talk about here is are essentially database views and certain concerns that database views have in terms of performance degradation. So first of all, a database view can be formally defined as uh, a, a result set of a stored query on the data, which the database users can query just as they would in a persistent database collection, right? So what essentially happens is, if you have a table, uh, you run a query, and the results of those query persist in one manner, and that can act as as an individual table, and would give you almost all of the features just as any database table would. However, in terms of the exact implementation of database views in SQLite, those are only read. So database views in SQLite are read only, with certain exceptions. I have posted. I've added this link here, but this happens only under certain conditions. So under most circumstances, database views are read only and are updated whenever the underlying table changes. So essentially, if you see, what's happening is, transitively, whenever the actual database table changes, this query would rerun and this table would get refreshed. So essentially, there's some more processing power always being consumed. And while database views are great for readability and flexibility in terms of code structure, particularly when we talk about SQLite, SQLite does not support an equivalent implementation of what other database systems such as Postgres have. They have something known as a materialized view, which provide developer the ability to handle as to when the schedule when the refreshing schedule of the view would work. So currently in Android and so basically in SQLite, whenever you define a view and the underlying table changes, uh, the view also changes automatically. But since every time you're running a query and you might not even need the results, this would cause performance degradation to some extent. So while we don't have a solution as of now, in case views work for you, that's great, but make sure that you are analyzing them well and they're not causing performance degradation. uh, right. Thanks a lot for attending, and uh, yep, that's that. You can feel free to reach out to me on any of these channels if you in case you have any queries regarding this or anything in general. uh, Thanks a lot, Sid.
Yeah, I'm here. Yeah, so I think we can then take up questions. Rashanjyot, by the way, amazing talk. These are topics that need to be discussed. I especially like the re-emission one on the invalidation tracker, where you're running a function over the stream. So it's a very common use case, and I think the questions also reflect that. Like our audience has some questions about exactly some of these same things. So let's go through them.
Sure. All right. Okay, I think we're going to do. Okay, we'll go top down on that. So first question is from Chetan. What's the realistic limit on SQLite to be slow for querying? Oh, okay. So since optimization is just a battle, so there's no end to it, first of all. And when you say realistic limit, it all depends upon how you're storing your data. And as it depends upon essentially how your data is structured, how you query it, how frequently do you update it. So, for instance, sometimes there are read heavy use cases, sometimes the use cases are write heavy. So, I think there's no one silver bullet answer for this. It really depends on the use case, and that is why a lot of what we talked about in this talk might be relevant to and might not be relevant to you, and as per your use case. So it totally depends, and depending upon the use case, probably you'll have to figure out the best fit.
Cool. Let's take the next one.
Right. From your experience, what type of apps hold such an amount of rows that it justifies optimizing query performance? Well, okay. So I can share my experience at my current organization, OK Credit. We are building uh, a credit ledger system, a credit ledger maintenance app for India, and SMEs all across India. And our app works almost every feature of the app works offline is offline first, and the amount of data that the app has, because it works offline first, is really huge. So we faced performance degradation personally in a lot of use cases and improvised it. We figured all of these issues with database views and in terms of query performance. I'll give you a simple use case and a sample example which probably everyone could relate to. uh, I guess everybody must be familiar with messaging UIs where, for example, WhatsApp, Facebook, Instagram, where you have a list of contacts and you have messages, and essentially right below the contact name, you see the last message, and maybe the last message that was shared between you. So if you let's say you have 10,000 friends on Facebook, and with each of them, let's say you have shared hundreds of messages, right? So you have to, and on that screen, the complexity of fetching that last value becomes it becomes really complex to fetch that value. So proper indexing or proper appropriate query performance is required, else there will be significant query performance degradation. In our use case itself, we spent quite some time. In fact, the UI took a lot of time to be rendered. It probably reached out to quite a few hundreds of milliseconds, but then we improved this. So yeah, very much our app and pretty much any messaging app that you popularly use. All right. Let's take the next one. What are the best approaches for SQLite database security end to end? Uh, while I might not be the best person to answer this, there are certain steps I can share with you that some of the people within our organization have taken, and something that I'm aware of. You can go ahead with SQLite database encryption. if that helps. You might have to skip out on skip out from support from certain libraries, but encryption probably is one of the things that you could do. But probably that's not an area of expertise or an area that I've explored much. Uh, but I'll be glad to know if you could share something around it, or maybe if I have something later, I'd be happy to help. All right. Uh, Next up, do you have experience using SQLite? No, not really, but I'm really interested in it. In fact, one of my fellow developers had introduced me to SQLite, but I unfortunately haven't tried Kotlin multi-platform or SQLite or any of such platforms yet. I'm not even sure. So yeah, currently I'm just stuck to Room. And is so how does it compare to Room or this? Yep. So I'm sorry, I'm not the right person to answer this. Okay. Can we use the same patterns and performance improvements with Room? Absolutely. In fact, Room is okay. So I'm not sure who needs to hear this, but Room is not a database. Uh, Wherever I posted about my talk, a lot of people mentioned that you should instead use Room instead of SQLite. So Room is just an ORM. It's just an object relational mapper. It is an interface to access SQLite. Android natively supports SQLite. SQLite is the native database that Android works with, while you could add in different databases such as Realm or Mongo or maybe several different databases, right? But SQLite is what is actually running under the hood. Room is just an ORM, and Room, and that is why we discussed about the limitations of Room, because it does not support everything in terms of the interface wrapper that it exposes. SQLite is far more powerful, and if you compare SQLite to other sophisticated databases systems such as MySQL or Postgres, even then you'd feel SQLite is even less powerful there. So SQLite is sort of, I mean, this might not be an absolute right thing to say, but SQLite, as the name suggests, is a lighter version of most SQL databases. It sort of is a subset to them, but still really powerful. Uh, but yeah, to answer your question, Room is just an ORM, and under the hood it uses SQLite. So yeah, everything is relevant for Room as well. Okay, how can you measure SQLite performance in production? Interesting question. You can always have analytics set up for that. Query perform that so You can log query performance times to your analytics if you have added one, or you can integrate analytics into it. That's, I guess that's one way to do it. Another thing is before moving it out to production also, I guess exhaustive testing in terms of populating data well enough, and extrapolating your scale. If your scale is x, extrapolate it to 10x or 100x or whatever you think could scale well, and then test for it. And yes, for production use cases, I think logging and analytics should help. In Android okay, the next one is from Rajesh. In Android application lifecycle, at what phase or stage we should create indexing in terms of integration using Room? Okay. Uh, so essentially, you would. That's a great question. In fact, I would want to first take up another thing here is in whenever you find a use case, whenever there's heavy deletion or heavy insertion, you might also want to consider dropping the indexes first and then recreating them, uh, just as we had this example of the transaction. So whenever you're adding something to the database, updating it or deleting it, essentially index is also updated. So there is a cost involved. So whenever you're performing heavy deletes or heavy insertions, there might be a case that you would be better off dropping them first and then recreating them after your insertions or deletions or updations are done. And now to answer your part of question, Sid, Sid, I have lost the question. Can you help me redirect to it?
Yeah, he's asking, Rajesh is asking, like, at what part of application
Right.
lifecycle? I think he's asking at what part of development of an application
Right.
you start, or like during the runtime. I'm not
Right.
sure what he's
Uh,
asking.
Right, got that one. Actually, I just scrolled up a little. Anyway, thanks for that. So, in Android application lifecycle, at what phase or stage? This again depends upon whether a lot of queries are actually running on the same database connection or not. Another thing to note here is: are you using a singular database connection, or are you using multiple database connections, or even are you using multiple databases within your app? So there's always going to be this performance versus memory footprint trade-off that you have to take care of, and depending upon whether whenever you think you're not performing a lot of memory intensive operations, probably that is when you should deal with this. And more or less creating indexes during migrations or dropping them during migration should really help. Probably that's a step to go forward, because whenever your app is launched, migrations are taken care by the system itself. Yes. Okay. And then the next one is there any tool to measure SQLite query response time in Android? Um, I'm not sure if there's any tool. And when you say tool, there are one is any tool for production, and another is in general when you're dev testing. So for testing and for non-production environments, you can use SQLite shell, and you can have this something. There are certain libraries. I am probably forgetting the name. I can just check and get back. I think it's SQLite time. Maybe I'm not sure. Maybe you can just have a look and search online. But yes, you can use the native SQLite shell as well and you can log all of these in the logcat uh, as well to check that. For production environments, probably logging and analytics should help there. Uh, Now regarding next question, how do you deal with indexes when doing data migration? Yes, great question, Asha. So essentially, while we are doing migrations, it depends if what sort of changes we are doing. So we certainly add or drop or update indexes during data migrations itself. In general, yes, that's how we do it. But how do you deal? Essentially, it depends upon within the migration. Are we changing a lot of data? Are we removing data? Or I mean, what are we doing? It depends upon a lot of meta factors that are whenever you're creating or deleting an index, potentially there might be other meta things that you're doing with the database tables as well. So without the complete picture, it is difficult to mention as to if there's a singular way of how to deal with them. Okay, it's the next one. Querying DB with filter or sorting. Querying DB with filter or sorting query versus observing all data then performing a filter correction. Which one do you prefer? The first one. And great question, Chetan, because in production, in fact, I feel there have been certain times that we have been observing all data and then performing map of filter collection, and but then you have to understand what's happening. One is the application layer and one is the database layer. Essentially, if you're pulling out all of the information from the database, what you're doing is, first of all, there's more payload that is being transferred, so it'll create more of your Kotlin or Java objects, right? So those objects will stay in memory, and while you don't need them, because essentially you would filter them out later, but they have now entered the memory and they certainly have a memory footprint. And eventually you'll and if you're under a really your app is under a memory crunch, a GC would be called, and probably there could be a GC call, um, and your app would certainly feel a little more sluggish to the user. So the right way, or the ideal way to do it, would be querying the DB itself with the filter. But I understand, because from a developer perspective, it's when you're more familiar, because that's where in fact the stock comes in. I marked this talk as intermediate, but I feel for a backend developer, this talk would have been a beginner level talk. However, for Android developers, what generally happens is we prefer getting all of the data onto the application layer and then filtering it. But that's probably not the right way to go ahead. If your data is huge and scaled up, probably that's not the right way to do, and probably you should switch to querying within the DB itself. Right. So the next one is answered already. What data structure does SQLite use for index? Right, we mentioned. So this was mentioned. So SQLite uses B trees, which are balanced trees. The formal definition for balanced trees is they are binary trees where the difference between where the uh, traversal length from the root till the leaf node For any leaf node is not. So I think I'm sorry, I jumbled a little. So the traversal length from the root node to the leaf node for any given leaf node would the difference of those lengths would never be greater than one. So it'll be balanced in that manner. In fact, I will share a link here as well, a great link which mentions as to how it is internally created and how it gets updated. In fact, that's present as part of the slides as well. I'll soon be sharing the link to the slides. Probably Sid could help me with that later.
Yeah,
Right.
definitely.
So next question is from Rohan. Any example of dealing indexes for data migration? Right, certainly. So, for example, let's say you're adding a new column to the table, just as we added in this use case, right? Earlier we only add amount, and then we later add tax as well. So now let's say your country introduces us some sort of tax, and you have to add that column, right? So and you might want to create a new index for that, or maybe drop certain indexes because those have become stale and your logic could no longer operate on those. So yes, it was fairly contained in the current talk as well. Next one is SQLite versus Realm for mobile. Which of them will you advise for production ready app? Again, such questions do not generally have a silver bullet answer. I have personally used Realm, and I'll be honest, I am a much huge fan of Realm and Mongo myself, and personally like vouching for them to become much more popular, and especially after Realm and Mongo got merged. But anyways, since there's no one silver bullet, you should always understand that SQLite is natively supported. While for Realm there would be certain space concerns because you'll have to add that as a library yourself. That's one major big concern for bigger applications. Even a couple of kilobytes matter a lot, and that's something that we do all day long. Another thing is it depends really on a use case. Do you really have a use case for NoSQL? It's more of a call of NoSQL versus SQL. So there's no one single advice as to whether you would use one for production or not. In fact, I also happen to know an application which has a valid use case of using both of them together. So not really one answer. I think it's about SQLite versus no SQLite, and that can be answered only as per your particular use case. Right. So I think Sid, we have covered all of the questions. Do
I
you
think
think
we have
next?
we have three more. So you can select the view sorting and just
Right.
select unanswered. So you'll see three questions.
Right. Thanks for that. Okay. So next question is from Shrikant. What is the best practices to store image in SQLite base 64 or blob? Right. I probably am not the best person to answer this because more or less in my personal experience, whenever that has happened, we have preferred storing them as files rather than as base 64 strings or within blobs. But base 64 essentially are also character streams, so they can be stored as blobs or text. And one thing for sure, that you will certainly have to convert those eventually to bytes, so there will be a conversion overhead at that time. And great that this question just came up, because I guess the last question was about using Realm versus SQLite. One of the things that I've realized is that NoSQLite databases are really great at storing heavy byte carrying information such as videos, media, in textual character stream format, and they are much more optimized for it. So that's one great valid use case. If you have, I'm not sure who was the one in the last who had this last question, but yeah. All right, next up, how do you usually decide whether optimization through indexes, etc., is actually worth the effort, assuming expected size of the DB is a big part? Right. So I think it's more of a mindset thing, right? Are you going for a premature optimization? Are you a follower of Yagni? You only want to do it when you face a problem. So I think it's more of an individual or an organization, or essentially a collective mindset call that you have to take. You can be preemptive about certain problems that can come up, or you could probably solve things as and when you go. So that's again a mindset thing. But essentially, just a second, I again lost that question. I think that got marked answered, right?
Yeah, I'll mark it unanswered. You can see it.
Right. Sid, it would be great if you could just. Okay, cool.
Yeah.
So, So it's worth the effort if you certainly can extract out any impact from it. I think as developers, mentioning that we say that this query ran 20 milliseconds faster is probably not the right way to go ahead. If you can justify the business impact, or if you can essentially justify as to why that little time that you saved off helped you or improved your user experience, I think that's one way to decide if you want to go ahead and do that or not. In fact, there are certain things that you can go ahead apart from indexes and do that. Probably, if just talking in variably, not about just SQLite but other database systems, there's partitioning, or there are I mean there's of optimization. There are pragma commands, so you can move into those directions as well. But only if you need it. If you don't need it, probably an index is also something that you don't need. So it totally depends upon what your end goal is, right? Do we have a secure DB like SQL Cipher that supports coroutine? So SQL Cipher, I'm not sure about this, but I mean, I can just collectively recall, but don't take my word for it. I might be wrong. I think we recently so I know somebody who integrated SQL Cipher, SQL Cipher for encryption, and yes, I guess that supports coroutine. But I guess that's a question that you could probably search online for a much more concrete answer. But I guess I'm almost pretty sure that it does. Uh, and I think when you say it's a DB, so I think SQL Cipher is just a library to encrypt SQLite, and I guess it's not a separate DB in itself. Yeah. So any example of SQLite feature which is not available on Android due to SQLite version? Yes, yes, pretty much. So I guess the last version on Android is 3.32, which is supported. Uh, I guess I might be wrong, but there are certain features in that was released in 3.8 3.80 something in SQLite, which are not currently part of Android. And they I mean, I'm not able to recall the exact features, but probably I can just share that list soon. What you can do, in fact, in a much better way is you can follow the change log. They always publish a change log whenever a new version is released, so you can find out a lot of great stuff that they're putting out. Right.
Cool. I think that is the last question. And Rashanjyot, thanks for this amazing talk. It's a really amazing talk. We learned a lot about optimizing databases, some of the actual use cases where you would need to optimize and run these, a bit of these techniques to get the maximum performance out of your database. And you answer the questions as well. A lot of questions from our audience today. And I think that will be it for the session. In the next one, the next sessions that we have a short break of I think 30 to 45 minutes, and then we are going to have two more sessions. And if you like this session on the databases, you will like the next one because it is on full text search, but this one is in memory, so rather than reading it from database. So Kshitij is going to talk about that, and the talk after that is on improving your quality of your Firebase project by William. So these are the two upcoming talks in the next couple of hours. Take a break, hang around in the rooms, chat and network. And like I said, you can go to the Android Worldwide Slack workspace and then connect with our speakers, which is Rasanjot and Anna so far, and again ask these questions. So thanks a lot, and we will see you in the next